Thanks very much, Ian, my fellow countryman, and thanks to you and to Mark for inviting me back to wonderful Huntington Beach and to share with you some of the work that we've been doing in Cork in the very south of Ireland for well over a decade now, implicating the gut microbiota in relation to brain and behavior. You can see the title is a little bit different than what's in your book, but those of you fascinated by midlife, I will get to midlife too. Okay, there's my disclosures, nothing of note. Okay, so like many of you, I work in a medical school, and in medicine, everything more or less comes back to Hippocrates. And Hippocrates is thought to have said, now it could be fake news, but he's thought to have said that all diseases begin in the gut. Now, that can be quite surprising when you start talking to your psychiatry friends like Mary, who won't be surprised, but many of her colleagues would be, or neurology friends, or people in other aspects of medicine, because we compartmentalize the body as we specialize in medical training. And a lot of my neuroscience colleagues are often wondering why, if I'm really trying to understand the neurobiology of emotion, that I'm so fixated about what goes on in the gut. And again, all we have to do is look to our language. We use phrases like gut feelings, gut instincts. We make gutsy moves when we're brave. We're gutted when we're disappointed. We have butterflies in our tummy if we're nervous. So, perhaps there is some rationale to these phrases, which occur in many languages. Now, this guy is one of the heroes of my story. Every story needs a hero. So, and I bet very few of you will know who he is. I mean, I've given you his name, but will have heard of him before. Eli Mechnikov. Have any of you heard of him before? If you're immunologists, you will, but of course, because he's one of the fathers of immunology for his discovery of phagocytosis, for which he won the Nobel Prize in 1908. He was a Russian working at the Pasteur Institute in Paris. And like what happens to many great scientists later on in their careers, they often come up with crazy ideas, and Mechnikov was full of crazy ideas in his later years, and most of them are completely nonsense. But one of his ideas was, why did people who lived in what's now part of rural Bulgaria, why did they live longer and seem to live better? And he really wrote about this and tried to look at all of the aspects of their lives that might influence this longevity. And what he put it was down to what they ate. And what they ate was a lot of fermented foods containing lactic acid bacteria. So not only is he a father of immunology, he's a father of geriatric science in its early days, and a father of probiotics in many ways. And so if you go to Korea, you can get a yogurt drink which has Mechnikov's picture on it. So it must have that Nobel sign of approval and must be good for you, of course. But anyway, most of what Mechnikov wrote about in them days was forgotten about for 70 or 80 years. And he remained unknown outside of the immunology. Okay, so Rob introduced the microbiome, so I'm not going to go into that, except there's a few things just to remind. This is a teaching environment as well, so it's good, repetition is good. One of the things we like to remind you about is that we are living in a microbial world. Microbes were here long before humans. That's really important when you start thinking about it from an evolutionary perspective and how we have co-evolved with our microbial friends, shall we say. And perhaps, one of the key things to remember is that the weight of our microbes is roughly about that of our brain, which is quite humbling as a neuroscientist. We heard some of these figures already from Rob earlier, that we are more than 99% microbial when we think of all the genes that we have, which is also very humbling. And also we've heard in all the talks today about how fast moving this field is. And so if I'd given this talk a few years ago, I would have told you that we have 10 times more microbial cells than we do human cells. But this has been revised downward, and it's about 1.3 to 1. So we're still more microbial, but just about. And as I like to remind people, just think the next time you go to the bathroom and you get rid of some of your microbes, that you're becoming more human, and what that might mean overall. I don't need to remind you that this is one of the hottest areas in biomedicine, but I do need to remind you that when we talk about the microbiome, for the most part, we're actually only talking about the bacteriome, and we cannot neglect the other aspects of the microbiome, including the bacteriophages, the viruses, the fungi, archaea, etc., and there's lots of exciting work brewing up in that. It's made the cover of all the glamour magazines, as you can see in the lay press. Love it. And what my lab is really interested in is trying to understand the relationship that this microbiome has with our brain at key windows across the lifespan. In the perinatal period, I'll talk briefly about, in adolescence, in adulthood, and all the way into aging, and I will talk about aging as well. And what I'm interested in, and the one theme that has permeated my research over these past 2 decades, has been trying to understand the impact that stress has on our brain and that stress has on our body. And even here in lovely, idyllic Huntington Beach, it is not that difficult to remind you that we are living in a stressful world, and my desk on a good day looks like this. And all we have to do is, turn on our televisions, and we get more and more stressed all the time. Or in Europe, we start thinking about the future, and the future is, uncertainty is one of the biggest stressors we can have. And Ireland is looking very lonely here in this redrawn map of Europe. So stress is everywhere, and trying to understand the impact that stress has at key windows across the lifespan is really important. And to study stress-related disorders, like all disorders in medicine, we need appropriate animal models to really dig into the mechanisms about what's going on. And the one thing that I want to reinforce, and this is kind of a take-home message about stress, is that stress is a whole-body syndrome. It doesn't just affect a few neurons within the hippocampus in the brain, and we study these neurons, we love these neurons, they're fabulous, but it affects our immune system, and how our immune system talks to our brain. It affects our gut itself and changes gut barrier integrity and drives a pro-inflammatory phenotype in that way. And so when we're studying it, we have to think about it in a much more holistic fashion. And when I talk about stress, I'm really talking about traumatic stress or chronic stress overall. So I mentioned we need animal models, and we do, but they come with challenges. When we're trying to model complex aspects of human psychopathology, I really like this Far Side cartoon because it encapsulates the difficulties that we have, that we can't just put our mice or our rats on a couch and ask it about their childhood or whether they have recurrent thoughts of death or suicide. So we have to put our hands up and admit the limitations of the models that we work with. However, what we do know is that many of the key brain circuits that underpin the endophenotypic behaviors that are relevant to these stress-related disorders, like the fear circuits through the amygdala, the reward pathways through the striatum, have been evolutionarily conserved so that we can use animal models with some level of confidence that they'll tell us something about the human condition overall. So many years ago, over a decade ago, we were working on an animal model of early life stress. This is a model where rat pups are separated from their moms during the postnatal day 2 to 12. And then when they grew up, they had a whole body syndrome. They had changes in their immune system, changes in their brain chemistry, changes in their behavior, changes in their gut barrier function, in their mucus, everything as we would have expected. But what we didn't expect, and this was almost a serendipitous finding at the time, was that we found that there was also a reduction in the diversity of the microbiome in animals that had been stressed in early life. That there was a signature of this trauma that persisted in the microbiome. And that was quite a remarkable finding for us at the time. We've reproduced this now in other models of prenatal stress or later life stress. And also there's an emerging human literature, as Mary alluded to, coming from groups like Carolina Diverse group in the Netherlands, which is showing that moms with high perceived stress during pregnancy, that there is an alteration in the microbiome of the offspring that can be detected in the early life period. So this is really how we got into, from a stress neurobiology perspective, working on the microbiome. People are always asking me, how did you get into the microbiome? This was part of it, that and being based in Cork, where our microbiome centre is now in its 16th year, so we've been working on it quite some time. There are many factors in early life then that can influence this colonization. Chief among them, we know the mode of nutritional provision that babies born, that have breastfed have a very different microbiome than those bottle-fed. We know gestational age and prematurity affects the microbiome. I already mentioned maternal stress, but maternal infection, the environment we live in, the exposure to pets, antibiotics, hospitalizations, host genetics, all can influence the composition of this microbiome in early life. But perhaps the biggest or one of the most studied factors that influence the microbiome is the mode of delivery at birth. And this is becoming increasingly important because in parts of the world now there is 70 to 80% of the population being born by C-section. And in Brazil, in China, for example, in downtown Manhattan. I mean, it is becoming an issue once people start to realize that there might be some consequences. This is the initial study from Gloria Domingos-Bello, now at Rutgers, showing that there's a clear separation in infants born by C-section compared to those born vaginally. And in Nature last year, there was this paper came out, the TEDdy study, which looked at over 12,000 cases and clearly showed that both mode of nutritional provision and birth mode were two of the biggest factors they could see in discriminating the microbiome and early life. Just this week in Nature, there's one of the largest studies of C-section has shown the clear stunting of the microbiome, is the word they used, in infants born by C-section in a British cohort as well. So we're beginning to understand that there are changes in early life in the programming of how the microbiome interacts with host in infants born by C-section. We also know from epidemiology that there is an increased relative risk of asthma, allergy, type 1 diabetes in infants born by C-section. It's relative. We know very little about it in the context of brain health. And that's something that we've been interested in over the last few years. We've developed an animal model, and in this animal model, we were able to show quite clearly that there's enduring effects on terms of stress responsivity, immune changes, and in terms of deficits in social behavior that endured in our animal model. But that's in mice. What about in humans? So we did this experiment, which we actually never thought would work, where we took, I was going to say normal, but Irish medical students, and we decided to bring them into the lab and stress them in an ethical fashion. And you know, this is the problem with stress. How do you do that? Well, there's a really great model called the Trier Social Stress Test. And that's where someone is brought in and they're meant to give a public speech defending their dream job, and there's some hidden mental arithmetic tasks in it, and we're monitoring a variety of biological and psychological measures over this period. And what we found was when we stratified the individuals into, because everyone knows how they were born, they may not know the reasons underpinning it, but we were able to find that there was an exaggerated immune and psychological response to an acute stressor in these individuals, mimicking what we'd seen in our animal model, which was quite surprising given that there's so many things could have happened in the 22 years in between, and there are many other confounds that we have not been able to take into account. But it was telling us that there might be something related to this. But that's acute stress, which is fine. But what about chronic stress? So is there a way that we could ethically chronically stress individuals? Well, that's what's great about being an educator. We do this by subjecting our students to exams. And we can use the chronic exam period as a chronic stressor. And in doing so, again, we were able to find that there was subtle but significant increases in state anxiety and in the Cohen's perceived stress scale in individuals born by C-section. And that's really, again, validating what we'd seen in our animal models. What we're working on now is, because it's really important to note that C-section is a life-saving surgical procedure, is whether there are opportunities and windows that we can replace these missing microbes in early life, or dampen down the pathogenic bacteria that might arise through dietary or other nutritional approaches, and that's something that we're working on right now, and we have some exciting data in our animal models that we can do that, and that maybe we may be able to look at specific differences in how we manage a C-section individual versus a vaginally delivered one. Okay. So that's, some of the evidence that we have, but like my neuroscience colleagues are a very skeptical bunch. And that would not be enough to convince them that this microbiome is relevant. There are many other things that could be at play here. So how do you convince people that something is really important? Well, in engineering and biology in general, one of the best ways is to take it out and see what happens. And so the concept of being germ-free is not new at all. It goes back to Pasteur's time. And here you can see a germ-free man from this sci-fi magazine from the 1920s. Now, our germ-free mice have their own problems, but they do look a lot better than he does overall. And they essentially grow up in a bubble. Now, by growing up in a bubble, then they lack any real clinical translation, with the exception being perhaps the boy in the bubble that Paul Simon sang about. These mice in the bubble, though, do allow us to answer the question, is the microbiome involved, yes or no? And they're a starting point for a program of research that we've been have embarked on to enable us to do that, and have been very useful strategy to look at this overall. And so what we know is when you look at the brains of animals that grow up germ-free, you can clearly see a wide-scale changes in processes that are so important for normal brain development. We found some years ago now that myelination, now myelin is the key insulation on which nerve cells need to communicate appropriately, and you may know it mostly in the terms of demyelinating disorders like multiple sclerosis. Well, we found that there was hypermyelination going on in the prefrontal cortex of germ-free animals. We found there's increased adult hippocampal neurogenesis, the birth of new neurons, changes in neurotransmitters and synaptic plasticity. When we look at the arborization of these neurons, it's quite different. When we also look at the microglia, these are the brain's immune cells, the brain's macrophages, that they are unable to mount an appropriate response to an immune challenge. And indeed, work from the Karlinska has shown that the blood-brain barrier integrity is disrupted in these germ-free animals. And so almost all aspects of brain development and brain function that we've looked at have been changed in these germ-free animals. And you don't need to be a neuroscientist here to be able to clearly see the differences that occur. This is a neuron from the basolateral amygdala. The amygdala is a part of the brain involved in fear responses, in the emotional aspects of pain, and in social responses. And you can clearly see that there is a hyper arborization going on in these amygdala neurons, very much like it's already in a chronic stress state. When we look at behavior in these animals, what we find is that these changes translate to, as we would predict, changes in fear responses, deficits in fear responses. And when we put microbes back in, we were able to partially recover this. We're quite interested in irritable bowel syndrome, and in visceral pain is a core symptom of IBS. And what we found is these germ-free animals have increased visceral pain. And the good news was that we could actually rescue that when we put microbes back in post-weaning. And then finally, we looked at social behavior. And in all of our findings, we do find that the changes we see are much more prominent in males than females, which is quite striking, because in most stress-related disorders, we would expect it the other way around in terms of looking at sex-dependent effects. But so that led us to look at disorders where there are a greater male preponderance, which is like autism and adolescent onset schizophrenia, and they have social deficits at their core. And indeed, when we tried to test this in our germ-free animals. And mice, like humans, are quite social, so if you give them the opportunity to spend time with another mouse or an empty chamber, they'll gravitate towards the other mouse, but not if they're germ-free. And mice, well, like some humans, can be a bit fickle. So if you give them the opportunity to have a novel playmate versus their everyday playmate, they'll gravitate towards a new playmate, but again, not if they're germ-free. And so this has started us thinking about this in many different ways. But the core of it is that for normal, appropriate social interactions, you need to have appropriate microbes within your gut. We started looking at this then from an evolutionary perspective. And you start thinking about it, well, you know, in terms of what's in it for the microbes. And you can think, if you're in a crowded room like this, where microbes are being passed from one to the other and people are in a social environment, it is probably good for microbial fitness in some ways. And so I collaborated with Seth Bordenstein, who's an evolutionary microbiologist at Vanderbilt, and we put some of these ideas to Seth, and he told me that I was completely wrong. And every now and then, it's good to be told you're wrong, and that's why we need experts in the world to collaborate with. And the reason that I'm wrong is that I'd forgotten something that I've already told you, which is that we live in a microbial world. So microbes have always been there, and there's never been a time where the brain has existed without microbial signals. And so we have co-evolved, and in a way, these are our friends, and they do give us social benefits in that way. And so when you start looking at this across the animal kingdom, as we've done now in this paper coming out in Science, you start to really realize that anywhere you disrupt social interactions, whether it's in insects all the way to primates, you can change the microbiome. But the corollary is also true in terms of that if we mess up with the microbiome, we can interfere with social interactions that can drive changes in physiology and behavior across the animal kingdom. And this is still fields that are still quite early, but there's something about the social brain and the signals that it requires from the microbiome to mount an appropriate response. And the clinical connotations of that are still completely unknown, but there's a growing understanding that the microbiome may play a role in aspects of autism, in social anxiety, in the social aspects of schizophrenia as well. But the big question in the field is how? How could microbes in the lumen of the gut send signals all the way to the brain and affect these complex behaviors? Well, we're just about at the beginning of figuring that out. We know that the immune system is really important. We know that the vagus nerve, and I'll talk about that in a second, and we know that many of the metabolites that microbes make are very important. The vagus nerve in particular sends signals from the brainstem all the way to all the organs in the body and vice versa. So it's a bi-directional highway of communication. And some years ago, together with John Bienenstock's group in Canada, we were interested to see whether the vagus was playing a role in the behavioral effects of a selective bacteria. In this case, it was a lactobacillus. So we cut off the vagus route of communication, and all of the effects of this lactobacillus were gone. So this tells us that, at least in this case, that what happens in Vegas doesn't just stay in Vegas, but will actually affect our emotions in some ways. Now that joke is getting old. I was able to use it in the title of a paper this year, so I can soon put it to bed, but it really reinforces the importance that this neural pathway of communication is. But it's not the only one that we have. I mentioned already the metabolites. Well, it's worth reinforcing that the microbiome is a factory producing all kinds of weird and wonderful chemicals that our bodies wouldn't produce without it. Among these are, for example, the short-chain fatty acids. And so in a study in the last year, we were interested, well, could we just bypass the microbes altogether and just go to the metabolites? And so we did that in an animal study where we looked at short-chain fatty acids and whether they were able to have some of the same effects as parent microbes. And indeed, they did. They attenuated some of the long-lasting effects of chronic stress, both in terms of the gastrointestinal physiology, but also in terms of behavior. And so we're beginning to really see, and that's one of the themes you've already heard in the earlier talks, is that we can modulate the microbiome then by modulating the substrates, the diet, because these microbes are nature's medicinal chemists acting on the substrate. So if you can change the substrate, or you can change the microbes, and that will change what actual metabolites are being generated, and then how they interact with the various molecular targets within the gut and within the body in general. So I said that stress, especially in early life, changes the microbiome. We know that mice lacking the microbiome have exaggerated stress response and altered neurodevelopmental trajectories. And then that leads us to the question, could modulation of the microbiome have beneficial effects? And of course, the answer is yes. And in this slide, just shows that some of the strategies that we've been working on, both probiotics, specific prebiotics, postbiotics, which with the metabolites themselves, and even more recently, we've been working on fermented foods like milk kefir, and showing some really encouraging data in our animal models to show beneficial effects against stress-related disorders as well. So targeting the microbiome, at least in animals, is giving us some beneficial effects. I said I'd mention aging because aging is very pernicious time for the brain in terms of inflammaging processes that are ongoing in the brain, and we know that chronic stress then can be a kind of add fuel to this fire and lead to a variety of behavioral changes, including social isolation and depression and anxiety. And there's a growing literature looking at the impact of the microbiome in the aged population. This study from my colleagues in Cork some years ago showed that there was a reduction in the diversity of the microbiome as we age, and this was driven by a reduction in the diversity of the diet. And this totally supports what Metchnikoff had been saying 100 years ago overall. So we've been revisiting Metchnikoff's ideas and looked at the impact of aging in our animal models, and find that there is an elevation in intestinal permeability that's exaggerated following acute stress in our models, increases in inflammation, and changes in the microbiome. And then that led us to think, well, could we do anything about this? And so for this then I focused on midlife. Maybe because it's where I am, but also because we feel that it's a period where we might be able to intervene earlier and in a preventive medicine type of way. And so we found that in midlife, these are about 11 to 13-month-old mice, they already have these neuroimmune changes, increases in stress-induced immune priming, microglia activation, and infiltration of inflammatory monocytes. And then we decided to treat with a prebiotic, inulin, which is widely found in vegetables like leeks and chicory and Jerusalem artichokes. And so we were able to dampen down a lot of these neuroimmune changes already by chronic treatment with this inulin, which is quite exciting. So maybe if anyone's thinking of having a midlife crisis, and this is the team and Marcus who did it, that rather than getting that motorbike, maybe eating more leeks might be a better strategy overall to get at this. And it's really encouraging in terms of what we're doing. But a lot of what I've been telling you has been focused on animal model work. The goal now is to move into human translation of this and towards the whole field of what we coined as psychobiotics. And this is a phrase that we've come up with to basically be a targeted intervention of the microbiome that will support brain health. We've expanded the criteria with our colleagues in Oxford to be basically any intervention that we know will affect our microbiome in a positive way. I put this in here to remind me to say that it's over 30 years since Tracy Chapman was singing about fast cars and revolutions, and in that period there's been very little innovation in psychiatry in terms of how we would manage brain health. And so we need to come up with a new revolution if you want. And so that we've written this book, The Psychobiotic Revolution, to really reinforce that it's time that in medicine that we did take nutrition into account, and that targeting the microbiome through diet might be a very beneficial way, but we need much more evidence to do that. Okay, FMT, you're going to hear a lot about this later today as well, but no microbiome talk is complete without it. And I just wanted to show that it is becoming much more mainstream. These are the capsules, and so we've put in with my collaborators in Australia, we put in a protocol to deliver capsules to patients that suffer from anxiety and depression. Only time will tell whether they will work. And we've taken the microbiome from depressed individuals and transplanted it to animals in this kind of translational way that Mary was alluding to at the end of her talk. And we were able to show that animals were able to develop many of the symptoms of depression, including increased anxiety, anhedonic-like behavior, and inflammation, which was really remarkable because this is helping us get towards causality in the studies that we do. Again, from a human studies point of view, could we reproduce anything we found in animals? Well, this was another approach where we took a group of healthy individuals and gave them a strain of bacteria, bifidobacterium, that we had shown in our animal studies to have a lot of efficacy in terms of anti-stress effects and pro-cognitive effects. This is a small study, but we were able to find that it did dampen down the stress response and that there was a defined EEG signature. This is Andrew, the psychologist on our team, that looked at it. Paul Enk's group in Tübingen were interested in, in this approach. They do human brain imaging, and so they came to us to ask, well, could they look at what strain would we recommend, and we recommended the same strain. This is just published a few months ago, and they did a cyberball task, which is basically where you're in a scanner and you're playing a ball game with two people in virtual reality, and all of a sudden they stop playing with you and play with each other, and you become excluded, and your brain doesn't like this, and it feels stressed. But if you'd taken this bifidobacteria, you didn't mind. And so it's nice to see some validation of what we've done. However, we also took our most efficacious study from our animals and tested in a similar strategy in our lab, Lactobacillus rhamnosus, and you cannot get more negative data into the one paper if you tried. It did nothing. So that's, that highlights some of the problems and challenges we have in the field, and these are not specific to the probiotic field. These are in everything that we do, but we need to also have publish all the negative data that we get, because it's really important in what we're doing. The field of depression in the microbiome is changing. This paper that came out in April is really exciting because they looked at a large cohort of 1,000 people and were able to identify a clear microbial signature, and then validate it in a second cohort from Groningen in the Netherlands, where they didn't have depression scores, but they had quality of life, and were able to validate it and in a small group of treatment-resistant patients. So we're beginning to see that in depression there is what I call an unholy trinity, speaking to my Irishness, of immunity, stress, in the microbiome, and that any treatment for that needs to be able to tackle all aspects of it. And the last thing I want to say, and just remind people, because we're a mixed audience, is that it's not just in stress and psychiatry that the microbiome gut-brain axis is going to play a role. We're seeing an evolving trend in neurology as well, and this is really exciting. If someone had told me that in diseases like ALS, where the microbiome now is being implicated for the first time, but also in epilepsy and Alzheimer's and Parkinson's disease, and this is really exciting overall, but only time will tell how much we can do that. And so the whole goal in medicine has been, in the 20th century, about killing microbes and killing germs, saving millions of people at the same time. But now we realize that the beneficial effects that microbes will have on our health, and that our state of gut will markedly affect our state of mind. This is the work of a big team of people. A big shout out to my clinical colleague, Ted Dinan, who's just retired as head of psychiatry in Cork. And we're back to Hippocrates. He's also thought to have said, again, it could be fake news warning, let food be thy medicine. And I'll just change that to maybe to let food for your microbes be your medicine. And I leave you with this cartoon the dreaded Daily Mail made about us. So thank you very much.